1.3 Lesson 1, one type of integral of a function. Our objectives for today's lesson are: 1, you will have a conceptual understanding of a definite integral. What is a definite integral? You will understand that. And what can we use it for? You will also have an understanding of that. Objective 2, you will be able to estimate the value of a definite integral of a function on an interval from a to b by using the graph of the function. So for today's lesson, we will look at 2 examples. And vocabulary for today's lesson: definite integral, integrand, lower limit of integration, upper limit of integration. Both of these together are called the limits of integration. Integration with respect to. So now we will look at an example for Objective 1. You will have a conceptual understanding of a definite integral. What is a definite integral? What can we use it for? Let's take a look. So here we have a problem, and the problem states the graph below shows the velocity of a passenger jet in miles per hour from t is equal to 0 hours to t is equal to 5 hours. So at t is equal to 0 hours, it's leaving the airport. So maybe it's like on the runway getting ready to take off, and then it starts moving and it takes off, right? So at the instant that it's getting ready to take off, the plane is stopped and then it starts moving. So the plane starts at a velocity of 0 miles per hour, but then it accelerates on the runway, and then it lifts off, and then it's in the air, and then it goes faster and faster and faster. And after some time, it reaches its cruising velocity of 600 miles per hour. It cruises at that velocity for some time, and then it starts to approach its destination, so it starts to slow down. And then as it is slowing down, it gets closer and closer to the runway. It lands on the runway and then comes to a stop at 5 hours. So that's basically what's going on. So on the horizontal axis, we have time in hours from the time the plane starts to move on the runway from the airport that it left to the time the plane stops on the runway at the airport that it arrives at. And on the vertical axis, we have the speed of the plane, or we can say the velocity of the plane, measured in miles per hour. So the graph shows the velocity of a passenger jet in miles per hour from 0 hours to 5 hours. The question that we want to answer is, how far does the plane travel from t is equal to 1 to t is equal to 4 hours? So if you look at the graph here, we have t is equal to 1, and here we have t is equal to 4. So on that time interval from t is equal to 1 to t is equal to 4 hours, we can see that the velocity of the plane is constant. It's cruising at a velocity of 600 miles per hour. And it does so for a length of time that is 3 hours. From 1 to 2 hours is 1 hour, 2 to 3 hours is 1 hour, and 3 to 4 hours is 1 hour. 1 plus 1 plus 1 is 3 hours. So we know that distance is equal to rate times time. And since the rate, or the velocity of the plane, is a constant value for the time from 1 to 4 hours, this is a very easy problem to do. We're just going to say the distance traveled is equal to the constant rate, which is 600 miles per hour, multiplied by the total time, which would be 4 minus 1, which would be 3 hours. And if you look at the units here, when you multiply miles per hour by hours, hours and hours will cancel, and that gives you the distance traveled by the plane from 1 to 4 hours, which would be 1,800 miles. So we'd like to make the observation that the calculation that we made to determine the distance traveled by the plane over a period of 3 hours was to take the rate and multiply by the time. And if you look at the graph of the velocity function, this calculation that we just made is equivalent to finding the area of this rectangle that I'm about to draw. So on the time interval from 1 to 4 hours, we have a length of 3 hours for the time. And on that time interval, the velocity of the plane was fixed at 600 miles per hour. So if you look at what we did, we multiplied 3 hours by 600 miles per hour. mph for miles per hour. So if you look at this rectangle that I just sketched, when we found 3 hours times 600 miles per hour, it was in fact the area of the rectangle that I just highlighted now. So this calculation that we did was in fact equivalent to finding the area under the graph of the velocity function above the horizontal time axis between x is equal to 1 and x is equal to 4. So that's what we did. And we can notate that with a new notation called a definite integral. So we can notate this calculation with a new notation called a definite integral. So we will have the definite integral of the velocity function taken with respect to time on the time interval from t is equal to 1 to t is equal to 4. What is this equal to? It's equal to what we just did earlier. It's equal to the area of that red rectangle. And how do we interpret this? When you do unit analysis, you can see that this is going to give you a product whose units will be miles, telling us the distance traveled by the plane over a period of 3 hours. So this is equal to 1,800 miles. So now we will do some vocabulary development. The whole thing is called a definite integral. This part is called the integrand. The 1 is called the lower limit of integration. This 4 here is called the upper limit of integration. The 1 and the 4, when we consider them together, are called just the limits of integration. And the very last thing that we want to look at is, what do we mean by integration with respect to? So we say we have integration with respect to t in this particular problem. And if you look at the definite integral as a product, you're taking velocity and multiplying it by time to get distance. So that's how you understand where the integrand is coming from and what the dt represents. It would represent a change in time in our case. And again, to reiterate, what we have here is a product, velocity times time, to give us distance. Since the velocity of the plane was constant on the time interval from t is equal to 1 to t is equal to 4 hours, we were able to find the exact value for the distance traveled by the plane on that time interval. And in fact, this is just an algebra problem. You just multiply rate by time, and you get the distance traveled. But where does the calculus come in? The calculus comes in when you have velocity that's not necessarily constant, but perhaps it's variable. So in fact, that's what we have for the plane, not on the time interval from 1 to 4 hours, but if you look at what's going on before t is equal to 1 and after t is equal to 4, you can see that the velocity of the plane is variable. It is changing. From the time it leaves the runway to the time it reaches its cruising velocity, the velocity is increasing. And from the time it starts to decelerate until it comes to a stop, the velocity is decreasing. So if I wanted to change the problem and I wanted to know what is the distance traveled by the plane from the time it took off to the time it landed, from the time it started moving at the airport that it left to the time it stopped at the airport of its arrival, I could do this. I could find the definite integral of the velocity function with respect to time on the time interval from 0 to 5 hours. And of course, it would be 1,800 miles plus, what would I add? I would add these two areas. The area that I'm shading in green now, which would signify or which would represent the distance traveled by the plane from t is equal to 0 to t is equal to 1 hour. And I would add to that the area of the region that I'm shading in gold now, which would signify or represent the distance traveled by the plane from t is equal to 4 to t is equal to 5 hours. So I'm going to add to that the area of the green region and add to that the area of the gold region. And the sum of these three values would give me the distance traveled by the plane on the time interval from 0 to 5 hours. One thing to note is that we may not be able to find the exact distance traveled by the plane represented by the green region because the velocity curve on the time interval from 0 to 1 hour is a curve, and we may not be able to find the exact area of that region. But we can approximate it because it looks almost like a triangular region, so we could approximate the area of that region. And the same is true for the other region. We may not be able to find the exact area of that region. Why not? Because again, the velocity curve on the time interval from 4 to 5 hours, it's not a line segment, but it's a curve. So this looks almost like a triangular region, but not exactly. But we can approximate the area of that region by, for example, using the formula for the area of a triangle. So at this point in time, probably we're going to end up with an approximation for the distance traveled by the plane from 0 to 5 hours. We were able to find the exact distance traveled by the plane from 1 to 4 hours because the velocity function on that time interval was constant, but on the time interval from 0 to 5 hours, we will settle for an approximation just because at this point in time, we're not quite sure how to find the exact area of the green and the gold regions because the velocity curve on each of those time intervals is not a line segment, but a curve. Before we move on to our second example, let's revisit the lesson objectives. You will have a conceptual understanding of what a definite integral is. So you should understand that, for example, in the context of the problem that we looked at, the definite integral represents the distance traveled by the plane. Of course, you can have different applications, different word problems, and the definite integral could have different meanings. But one thing that you want to walk away with is the idea that the definite integral is representing some kind of a product. In this case, velocity times time. And it's useful, especially if you don't have a constant value for the velocity over your time interval, so that you can still think about, for example, in this case, the distance traveled by the plane on a time interval where the velocity may not be constant. So you should have a conceptual understanding of what a definite integral is. It involves a product. And number two, objective two, you'll be able to estimate the value of a definite integral of a function on an interval from a to b by using the graph of the function. I could have done an estimation. I talked about how we might be able to. So how could you estimate, for example, the green area or the gold area? I mentioned using the formula for the area of a triangle. Each of those regions are not exactly triangles, but they seem pretty close. So you could use, for example, 1/2 base times height and find the area of each region that way and get an approximation. So now we want to continue with objective 2 by looking at another example and another way of thinking about how we can do objective 2. So here is objective 2. You will be able to estimate the value of a definite integral of a function on an interval from a to b by using the graph of the function. And for that, we're going to look at problem number 1 from the exercises. So again, we want to look at this example for objective 2, which is to estimate the value of a definite integral of a function on an interval from a to b by using the graph of the function. So we will look at the graph of the function to approximate or estimate the definite integral of the function for part A and part B. So first of all, before I do that, let's go ahead and represent what we're looking for using definite integral notation. So in part 1, part A, we have the definite integral. Our integrand would be the function f of x. So we're going to have f of x. We're integrating with respect to x, and the limits of integration for part A would be from 0 to 5. And for part B, we're going to have the definite integral of f of x. We're integrating with respect to x. Again, the definite integral is a product. You want to understand that the definite integral is a product. So it is important that you write that dx to signify that what you have is a product. And in part B, we have the definite integral of f of x with respect to x from x is equal to -1, which is the lower limit of integration, to x is equal to 6, which is the upper limit of integration. And of course, for each of these, I can replace f of x with what I know f of x to be. What is f of x in number 1? Negative 0.1 x squared plus 7. So put that in parentheses, and then I have dx. So now, again, I can replace f of x with what I know f of x to be. Negative 0.1 x squared plus 7 and dx. So how do I approximate each of these definite integrals? We go back to the problem with the airplane. We understand that definite integral represents area under the graph of the integrand above the horizontal axis between the lower and the upper limits of integration for x. So let's go ahead and take a look at the graph of the integrand on the interval from 0 to 5 for part A. So we're trying to approximate the value of this definite integral in 1a. And of course, f of x is right here. And just to save space, I will just write f of x for the integrand because I know what it is. And again, how do we interpret the definite integral of f of x dx from 0 to 5? We interpret it as area under the graph of f of x. So here we have the graph of f of x that I will trace in green. This is the graph of f of x. I want to find the area under the graph of f of x above the horizontal axis between x is equal to 0 and x is equal to 5. So I am looking for the area of this region. And the area of that region is equal to the definite integral that I wrote for 1a. But of course, because the upper boundary of my region is not a line segment, if it were a line segment, I would have a trapezoid, and I could find the exact area of my trapezoid. But the upper boundary of my region is not a line segment. It is a curve. So the best I can do now is to approximate this area. And how can I approximate this area? One way, you have different ways you can do it, and we'll be learning additional ways. But one way is just to count squares. So approximately equal to, and you can count squares. If you look, for example, at what we have 0, 1, 2, 3, 4, and 5. And then here I have 0, 1, 2, 3, 4, 5, 6, and 7. So each of these squares that I'm showing right now represents an area of 1 square unit. The width would be 1 for each of the squares that I drew, and the height would also be 1. So width times height gives area. 1 times 1 is 1. So each of these squares has an area of 1 square unit. And how many of those squares do we have? Well, let's see how many we have. So altogether here we have 10, and we have 5 more here. So that's going to be 15. That's 20. Here's 21, 22, 23, 24, 25, 26, 27, and now the rest of them are not full squares. So I have 27 plus some more. How much more do I have? I'm just going to have to eyeball it a little bit. So if I put maybe this one is almost 1, and if I put these two together, they are probably going to give me about 1 square. So 1 plus 1 is 2. And if I put these two together, that's probably about 1 square. So that's going to be 3. And it's a little bit less than 4, maybe like 3.75. So plus 3.75 for the part that I shaded in gold. So this is going to be approximately equal to 27 plus 3 is 30, about 30.75. That would be the approximate value of the definite integral for part A. Now we look at part B. We want to approximate, or we want to estimate the definite integral of f of x dx on the interval from -1 to 6. So again, we understand that this is representing a product, and we're looking for the area under the graph of the integrand, which is f of x, and here's the graph of the integrand, above the horizontal axis, between x is equal to -1 and x is equal to +6. So we want to find the area of this region. And again, because the top boundary of our region is not a line segment, right now we can just approximate the area of this region. And there are different ways you can approximate the area of this region. Today we're going to start off really simple, just by counting squares. And just like we did for part A, we're going to count squares. Each of these marks that I'm highlighting now are 1 unit apart on the horizontal axis, and each of these marks that I'm highlighting now are 1 unit apart on the vertical axis. So each of these squares that I'm drawing now will have an area of 1 times 1, or 1 square unit. So altogether I have a total of 1, 2, 3, 4, 5, 6, 7. 7 more, so 7 plus 7 is 14. 7 more, so 7 plus 7 is 21 square units. And then we have 6 full squares, so 21 plus 6 is going to be 27 square units. 28, 29, 30, 31, 32, 33, 34, 35, 36 square units. And then the rest of them are not complete full squares. But I can estimate probably this one is close to 1 and this one is pretty close to 1. And maybe to compensate for the area that I'm missing, I can go ahead and maybe just count this little region here. So that's going to be plus 2 for that. And then if I put these two together, that's probably going to be a little bit more than 1, but I'll just say about 1. And if I put these two together, that's going to be about 1. So I'll write plus 1. And what am I left with? I'm left with maybe just this one here and this one here, this little region here. So that together might be about maybe about 1.5, maybe about 1.75 about, so 1.75. Have I taken care of every little region? It looks like I have. So now this is going to be approximately equal to 36 plus 2 is 38. 38 plus 1 is 39. And then I have 40. And then I have 41.75, approximately 41.75 square units. So if you wanted to put units here, you would just write square units, because this is representing area. There is no real-life context for this problem. So that's how you estimate the value of a definite integral of a function on an interval from a to b by using the graph of the function. And of course, there are other ways you can do it, and we'll get into that later, but this is what we're doing for today, counting squares. So today we looked at a couple of examples. The first one was a word problem, and that helped us to develop a conceptual understanding of a definite integral. A definite integral represents a product, and in the word problem that we looked at, the product was between velocity and time, so it gave us the distance traveled by the plane. And then we also looked at objective 2, where you are able to estimate the value of a definite integral of a function on an interval from a to b by using the graph of the function, understanding that the definite integral represents the area under the graph of the function above the horizontal axis between the lower and upper limits of integration. And we looked at estimating the value of a definite integral by counting squares. And of course, we focused on vocabulary.